right? I thought there'd be data. Is anyone out there?
Just like, la, 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 it's time, it's time. So we were talking about scale parameters and location parameters and scale invariant and location invariant statistics. So just as a reminder, theta is a location parameter if the PDF, obviously I'm talking about some distribution here. So if our PDF f of x and theta can be written as f naught, which is another PDF that does not depend on theta or probably any parameters, but I suppose it can depend on another parameter, definitely not theta. And you put x minus theta inside. So like the mu for the normal distribution, or the theta for the shifted exponentials we've been looking at. And these just shift distributions left and right. And we have a scale parameter. So theta is a scale parameter if our PDF can be written as theta, then some f naught that doesn't depend on theta, and then you have to put theta x inside. Now we saw an example last time, the exponential distribution with theta being lambda, that's a scale parameter. Okay, so then we talked about location and scale invariant statistics. So a statistic t, which is going to be some function of the random vector, is location invariant if so if you look at the function tx1 through xn, I'm just doing lowercase because I'm just looking at the function. I don't really care about the random variable. If this is the same thing as, like if you can go through and add something or subtract, because the c could be negative, and you'll get the same thing. So this is for all c, like for all real c. And then we saw an example last time of something that is location invariant, and that was for any, I did it for a uniform, but for any distribution, the statistic, a max minus a min, right? So you have all your data, and then you add c to all of it, and or subtract, if c is negative. And so the new minimum is just c plus the old minimum. And so the max minus the min is just a range, and it doesn't matter where you are. That's my point. Okay, and the final thing I have to refresh is the idea of a scale invariant statistic. So a statistic t is scale invariant if the t of x1 through xn is the same thing as t of cx1 through cxn for a c greater than 0. We have to say greater than 0 because like if you're looking especially at like a max and a min, negatives in front of them can flip things around, and the minimum would be the maximum. And so we can define this for c less than 0, but I just wanted to make it simpler. And the last thing I will remind you of that I won't write out fully is the idea of an inverse scale parameter, which is really just another scale parameter. But if you see a PDF f of x and theta, that can be written as like a 1 over theta times a PDF of x over theta. This is an inverse scale parameter, but it's really just another scale parameter if you reparameterize it and say, I'm going to let, tau be 1 over theta, then that's a scale parameter. Okay, so right now I want to prove to you that either if you have a scale parameter and a scale invariant statistic, then that statistic is ancillary, meaning its distribution is parameter free. Or if you have a location parameter and a location invariant statistic, that statistic is ancillary in that it is theta free. So which one do you want me to prove? Because the other one's on your homework. I actually typed them both in there, and I'm going to comment one out.
The first one.
I should prove the first one. Was my first one scale?
I don't remember.
I vote you prove scale.
Okay. So, okay, so if theta is a scale parameter, and this also would hold for inverse scale. So if it's a scale parameter and t is a scale invariant statistic, then t is ancillary. So on the homework that's coming out today, you're going to have to prove the same thing, but replace all instances of scale with location. And I'm just going to say that you can replace them all with inverse scale and it still holds, but I won't bother to write that down as a whole separate thing. So let's prove it. So I've got x1 through xn, and these guys are IID from some distribution. You know, often I write the joint PDF there to say this group comes from this PDF, but these are IID from this individual distribution, which can be written as theta times some f naught theta x, because it's a scale parameter. And so the joint PDF of x1 through xn, why am I suddenly doing that? We never use that notation. The joint PDF of f of the vector x and theta, we've got IID things here, and so this is a product of the f xi and theta. Using this, putting xi in for x and multiplying this out, you will get theta to the n and then a product as I goes from 1 to n, f naught theta xi. Okay, so I'm going to consider a new vector of random variables. So y1 through yn, where yi is defined as theta times xi. So these are also going to be IID. And if we work out the joint PDF for these guys, so the joint PDF for the y's is going to be, I guess I need just a little bit more notation, sorry. So I have like a y1 is g1 of the x's, and that is theta times x1. And so x1 being g1 inverse of the y's is y1 over theta. I don't know why I didn't do that with an I, because they're all exactly the same. So do the same thing for y2 with x2 out through yn. And I'm going to write down the PDF for the y's. So first, let me write the Jacobian. This is going to be the derivative of x1 with respect to y1, the derivative of x1 with respect to y2, on out, x1 with respect to yn, and then down here, xn, blah, 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 blah. Oh, I'm missing a y2, or I have that wrong. Okay, so this is going to be, we're taking these derivatives, and so we get 1 over theta all the way down the diagonal, and zeros everywhere else. And so the Jacobian is 1 over theta all to the nth power, or 1 over theta to the n. Okay, so let's find our PDF for the y's. And so I'm going to take the PDF for the x's and plug in the inverse functions and multiply by the absolute value of the Jacobian. And then because this is my joint PDF for the x's, this becomes theta to the n, the product as I goes from 1 to n, f naught of theta times yi over theta. And then this whole thing gets multiplied by the absolute value of 1 over theta to the n. And that first theta should be raised to the n, not. By the way, the scale parameter has to be non-negative. I did say that thing about the c, but because we're writing something with a scale parameter as, we want this to be non-negative. So if our scale parameter is negative, then this would have to be negative. So yeah, it does have to be because F naught is a PDF. So I forgot to say that in the scale case, theta has to be non-negative and also not 0, because a PDF equaling 0 is not going to integrate to 1. So because theta has to be non-negative, I can drop the absolute value over here, and I will. So I'll drop it, and then I cancel. Right, then I cancel that with that, and in here I cancel this with this. And the point is that the joint PDF for the y's is a product as I goes from 1 to n of F naught of yi, and this is theta free. So what? I'm trying to convince you that if T is a scale invariant statistic, then T is ancillary. So consider any scale invariant statistic T, and what? Forgot what I was going to do. Okay, so T is some little t of x1 through xn, and the x's are equal to the y's over the thetas. Sorry about the scrolling. So this is t of y1 over theta out through yn over theta. And so here I am just multiplying everything by 1 over theta. And so because it's scale invariant, it's just t of y1 through yn. And this is theta free, because this is just the function of the y's. And we determine that the distribution of the y's is theta free, and therefore ancillary. What? Or ancillary. Yay. I think the location one is even a little easier to show, because, I mean, it's pretty much the same, but the Jacobian is going to be identically 1 if you think about inverting what you have to invert there. It's not really saving you anything.
So, I guess I'm sure it doesn't matter, but would it be better to say that since this is equal to the t of the little x's, that is theta free? Or because the y's do involve theta, right?
The y's don't involve theta. You know what? I started with the theta here, but it did end up being a function that does not depend on theta.
I see. Since they're random variables that don't depend on the parameter theta, that's what we mean.
Yeah.
I
Yeah.
see.
So yeah, I should have made that more clear. This is a random variable, and this is a random variable. And because this is equal to this, and the y distribution of the y's is theta free, then the distribution of t is theta free. So
That
the
makes sense.
statistic is ancillary. Okay, so also true for location, which you'll get to show, which is really very, very similar. I could have done this whole thing using inverse scale parameters. So even though I didn't even bother to claim that, that's also true. And why do we care? Why do we care about ancillary statistics? Because I've got 2, I think, interesting facts for you. So why do we care? Too lazy to finish that question. Why do we care about ancillary statistics? So number 1 is, and I gave you a little spoiler about this last time. About to start coughing. Oh, okay, I gave you a spoiler about this last time. A sufficient statistic contains all of the information from the sample about the parameter. And an ancillary statistic contains no information about the parameter. So they're kind of like opposites in some sense. And so I claim that if S is sufficient and T is any parameter, I'm sorry, any statistic independent of S, independent of S, then T is ancillary. I guess this still doesn't tell you why you care about ancillary parameters, but number 2 in this list will, and we're gonna need this. Okay, so let's prove it. I guess, well, let me back up. What I really want is to be able to say a sufficient statistic and an ancillary statistic are independent. That would be great because things being independent make computations really easy. That is not entirely true. That is not true at all, actually. But number 2 on my list is going to be sufficient and complete versus ancillary. They must be independent. Okay, let me just prove it. So the joint PDF for all of the X's given the sufficient statistic, I should just say is, so this makes more sense, is theta free because S is sufficient, and that's how we define sufficient statistics. Okay, so now if you condense the data x1 through xn down to a statistic t, you're not going to be able to somehow get more information. You're actually reducing your information. So if t is t of x, so this could be the entire vector. It could be n-dimensional, it could be one-dimensional, it could be three-dimensional, just some kind of statistic formed from the data. Then, and I kind of want to say informally, so we've condensed the info, or maybe haven't changed it at all, and we won't gain information about theta, especially because our statistics are not allowed to depend on the parameters. So we won't gain info about theta. And so I can say that the conditional PDF for T given S is theta free. If I have all the X's and someone gave me S, I don't need all the X's. So I don't need all the X squareds. I don't need functions of the X's. So this is going to be theta free. And then finally, we have T independent of S implies, ooh. So let me do an aside. You probably already know this, but when you define independence in probability, you've probably started with sets and you said if they're independent, then the probability of the intersection factors into the product of the probabilities. And when you define independent random variables, you say that the joint PDF factors into the two marginals. Personally, I have never liked this definition of independence because I don't find it that intuitive outside of the idea that you can somehow separate things. My favorite I'm going to go back up there, but the way I usually define independence is I say either with sets or random variables, I say X and Y are independent if, so this is usually my definition, the conditional PDF for X given Y is just the PDF for X. And this is totally equivalent because on this side, we've got the joint PDF over the marginal. So it's equivalent to saying the joint PDF is the product of these guys. But I prefer this as a way to define independence, this guy right here, because I'm talking about the probability in quotes, right? If this is continuous, it's not exactly probability. The probabilities for X given Y are just the probabilities for X, like given Y told us nothing because there's just no dependence. And that's what I need to finish this proof off. T independent of S implies that the PDF for T is the same as the PDF for T given S. And we just reasoned that this is theta free. So we now have that the PDF for T is theta free, and that's the definition of T being ancillary. So we are done with that. All right, so here's one of my favorite theorems of all time. I mean, it's no Lehmann-Chevet, but number 2 on my list is a very famous theorem known as Bassu's theorem. And this is trying to be the reverse statement, but it's not quite true. If S is complete and sufficient and T is ancillary, then S and T must be independent. So this was what I was telling you about last time when I said, this is the most awesome thing that you will rarely use, but when you use it, it's going to be amazing. Because showing things are independent, especially if these are vector valued things, you're computing horrible joint PDFs and trying to show that it factors. And in a lot of cases, you just can't do that stuff in closed form. So this is a really slick way to show independence. If S is complete sufficient and T is ancillary, then S and T are independent. I mean, when you want to show two things are independent, you probably don't have one of them a complete and sufficient statistic and the other one an ancillary statistic. And that's why you don't use it very often. But I promise one day, look me up. Tell me you used it. Okay, so let's prove this. So consider the following function of little t and capital S. So consider, I don't want to call it a function. Consider this expression. The PDF for T with a little t minus the PDF for T given S with a little t and a capital S, just making that really grossly huge. That's a random variable. So this whole thing is a random variable, and the random part is the S. So you can think of the t, even though it's an argument of a function, as constant. Okay, so let's look at the expected value of this thing. So because in terms of randomness, this is a function of S, well, I don't even care about that yet. Let me first distribute the expectation. The first thing is constant. It's not a constant function, but it's not random. So its expectation is just ft a t. And the second thing is the expected value of that conditional PDF. And the random thing is S. So to do this expectation, I would integrate the conditional PDF and I would put in a lowercase s and multiply by the marginal PDF for S. Sorry, let me move this. DS. Because again, if you're looking to take the expectation of this, the only random variable there is S. So you need to put in a little s and multiply by the PDF for S and integrate over all S. Stop me if it doesn't make sense, but continuing on, if you take a conditional times the marginal of the second thing, that is how you get back a joint density. This is just kind of unraveling the definition of a conditional density. Again, because this is defined to be this over this. And so when you integrate over all s, you marginalize out the s, you get f of t minus f of t. And so you get 0. And I want to use completeness because what I have here is a function of s whose expected value is 0. So by completeness of s, we have to have this function minus ft given s, t given capital S equals 0 with probability 1. And so that means that ft is equal to ft given s, t given, and then I'm going to put in a little s and say that has to hold for all s on, so the with probability 1 thing is that this needs to hold on the set of points that capital S can take on. So for all s in the support of the distribution of s, like, you know, if this function is 0 every time you plug an integer in, and s is a Poisson random variable, so it is integer valued, then that's enough to say this thing is equal to this thing with probability 1. So it might not equal, they might not equal each other for certain s, for certain little s, but if they're not part of the distribution for big S, it doesn't matter. Okay, but look, this is one way to say that these random variables are independent. This implies that t and s are independent. Bassou's theorem. So I'm not going to do an example because it's not going to be useful unless I actually go through and show you that it's independent in another way. What I want to do is surprise you on the homework by having you compute something, maybe an expected value, maybe where it would be helpful if you could factor the expected value, and you can do that if two things are independent, and maybe you can say that from Bassou's theorem. So watch out for something like that coming up on today's homework. And yeah, I think we're done with this stuff. We're ready to start generic hypothesis testing, which is actually pretty awesome. I didn't like that first stuff. That's really boring. And I put that other hypothesis testing part in this course so that you already had time to absorb some of the terminology, like level of significance and stuff. So, and then I think this goes much easier once you've had time to let that sink in. So we are in hypothesis testing, general hypothesis testing, something like that. So this is where we're going to get kind of crazy. So we've got a parameter space, right? I've got an x1 through xn, and they have some joint distribution that depends on a parameter or vector of parameters theta, and theta lives in some kind of capital theta. A lot of times people write omega, but to me that looks like a sample space. I hate writing this symbol though. Okay, so and then we're gonna let this like capital theta not be a subset of capital theta. And we want to test a null hypothesis that theta is in some set theta naught versus it's in the rest of the space, which would be the complement, although you have to know that that's the complement with respect to theta. So I don't know if everyone has seen, I know a lot of you certainly have seen this, but I don't know if everyone has. So this is a set minus operation, which is the complement of theta naught within theta. So this just means theta intersected with theta naught complement. It's the rest of the space. And we want to test it well. We want to find the best test, the uniformly best test, the uniformly most powerful test. Okay, so before we get started, I wanted to say that defining a test is the same as defining a rejection region. And what I mean by that is, actually, before I write that, in hypothesis testing, you often hear about a critical region. And this is totally synonymous with a rejection region. The region in which your statistic must fall for you to reject the hypothesis. And so defining a test is equivalent to defining a rejection region or a critical region. Equivalent to defining a critical region, which is the slightly more grown-up way to say rejection region. Stats 101, you'd call it a rejection region. So what do I mean by this? Let me put a colon there, like I mean something. So maybe we're testing one thing, and I don't even want to set up some hypotheses. But we've seen many tests where we've done a test based on, say, a minimum and based on a sample mean. So if we have a test that says, I'm sorry, if our test says reject the null hypothesis if, say, the minimum in the sample is below some C1, and you do an equivalent size alpha test based on the sample mean, then you're going to say, I reject the null hypothesis if, like, say, X bar is less than some C2. So these are supposed to be two tests for the same problem, the same random sample, the same hypotheses. And now I want to write this as reject the null hypothesis if the random X vector is in a set C1 known as a critical region, where this is defined to be the vectors of X such that the minimum in that vector is less than C. So I'm kind of taking our rejection rule, which usually looks like one statistic and its relationship to some number, and calling it representing it as a subspace of n-dimensional space. And so over here, this is going to be reject the null hypothesis if the vector X capital is in C2, where C2 is the set of vectors such that the mean, I know that's probably a little hard to read because my first one's a vector and my second one is a mean, is less than C2. And I did mean for this first C over here, this little c, to be C1. So defining a test, what I was trying to say is defining a test is equivalent to defining a rejection region or critical region, because you can give me this result, or you can give me, I'm sorry, not that. You can give me this result, this conclusion, or you can give me the critical region with the understanding that I'm going to reject whenever the vector is in the critical region. And so we're going to move from talking about like best and most powerful tests to best or most powerful critical regions, because it's just sort of another way to talk about it. So like, what is the best critical region? It corresponds to the best test ever. And we need to define what we mean by a best test. So I think we're ready to do that. Actually, I have one more thing. But does this all make sense? This should be a bracket.
So I guess maybe when we say test, we usually mean a statistic and a critical region.
Yeah, it's just moving the region back to n dimensions though. You know, so every place that X bar is less than 7.1 consists of all the points X1 through Xn such that if you average them, it's less than 7.1. It really allows us to just really streamline a lot of things that are coming up to talk this way. Why? Because note that the alpha, the level of significance of a test, is going to be the maximum probability of making a type 1 error. And that means that you reject the null hypothesis when you shouldn't because it is true. And so now I can say this is the maximum probability that my random sample is in the critical region that I've defined when the parameter is theta and max over all of the theta in the null hypothesis. So now I'm translating from one language to another because X vector being in C means you reject. And so one more time, one test is better than another. We usually say this critical region is better than this critical region. So I'm going to define for you a best test, and building blocks, we're starting with, okay, so I'm going to define a best test for you in a very simple case, and that is the simple versus simple case. So consider the simple versus simple hypotheses, some null hypothesis that theta equals a theta naught versus an alternative that theta equals some theta 1. And obviously, you can't have those numbers equal. I guess you could, but no, you can't. It doesn't make any sense. So the, who is this by? Is this Neyman? I think this is Neyman's test. I have to check that out. Oh, this is actually not anyone's test. This is the definition. So here is the definition of the best test for those hypotheses. It's going to correspond to a best critical region. And so number one, remember again, because it's new, I just want to say this over and over again, the test is equivalent to the critical region. Best test, best critical region. So the first thing we need is that, I am so sorry, this is a mess. I want to say the best test specifically of size alpha. Okay, so the first thing we need is for it to be of size alpha. And because I have a simple null hypothesis, there's no maxing involved. So I need alpha to be the probability that the vector is in the critical region when the null hypothesis is true, which I can more simply say just theta naught, because there's no maxing. That just means it has size alpha. Number two in this definition will make it best. So the second thing is that the probability that, so where can we compare them? They have the same probability of making a type 1 error. We can compare them in their type 2 error. We want to talk about rejecting when we should. So the probability that X, I need to give notation for a best test. So I'm going to say C star is the best test of size alpha if C star has size alpha and that's supposed to be erasing. For any other test of size alpha, we're doing better when the alternate hypothesis is true. So if C is any other set such that it has size alpha, or level of significance, we need to compare them when the alternate is true. So I'm going to write the probability that the vector X is in C star when the alternate is true. So that means theta equals theta 1 because it's nice and simple. And I'm going to leave a space and then write the thing with C. So this is the probability you reject using this test when you should reject because the alternate hypothesis is true. And then the first thing I wrote down is the probability you should reject in the best test when you should reject because the alternate hypothesis is true. So you want that to be larger for any other C. So I really messed that up because I made it seem much more complicated than it is. Step 1, the test has to have size alpha. That means the probability you reject on the null hypothesis is true is alpha. And step 2 means if you compare it to any other test, then when the alternate is true, that is when you're putting in theta 1, you want a higher probability of being in the rejection region, higher than all other tests. Does that make sense? We can write this statement here in terms of power functions. And for that reason, this best test is sometimes known as a most powerful test. So this is a power function that's defined by the rejection region C star evaluated at theta of 1 greater than or equal to a different power function defined by a test with rejection region C evaluated at theta 1. And so from this statement, you say C star has higher power when the alternate hypothesis is true, actually higher than C and the highest possible power. So a best test is often referred to as a most powerful test. So you might hear best test, and this is equivalent to most powerful test. Best test, most powerful. We've only done this for simple versus simple so far, but again, building blocks. So I have a name. This is due to Neyman. It's Neyman Pearson.